Hi, and welcome to this short series of Psytrance tutorials in FL Studio. In this series we'll be covering three main topics: bass phase alignment, harmonic bass processing, and EQ cramping. Without further ado, let's dive in. I've got a small part set up here, a simple 4-bar loop with a kick and bass. Let's listen. I've got the kick and bass routed into channel 1 and 2 and sidescope loaded up to channel 3. First thing we need to do is route the kick and bass into sidescope using sidechain. Next, I need to open the plugin wrapper settings and click on the connection tab. This brings up sidescope's plugin routing, and we're interested in input 2 and 3. These are the plugin sidechain inputs. Route channel 1 here, route channel 2 here. Now press play and we should see the kick and bass waveform display across the 4-bar loop. The kick is shown in green and the bass is shown in orange. As we can see, there's a problem with the phase alignment on the first bass note. Where the kick is peaking in the wave cycle, the bass is at a trough. If we take two identical sine waves at the same frequency and add them, the result is a sine wave with an increased amplitude. These waves are said to be in phase. If we take one of the waves and flip the polarity or delay it by 180 degrees, the waves cancel each other out and we hear no sound. This is known as constructive and destructive interference. As the waves of our kick and bass are not identical, we instead get a drop in amplitude where the waves sum. The result is a thin and inconsistent sound to our low end. One way to improve this is by flipping the polarity of the kick. That already sounds better. I can now use this Vox & Go phase plugin on the kick channel to make some fine adjustments and line up the peaks and troughs. Let's listen as we flip back and forth. As we can see on the meters, there is a 1 dB drop when the samples are out of phase. When they're in phase, the wave reinforces, resulting in a smoother, more consistent sound. Thank you for watching and see you in the next segment. In this example, we're going to look at another way of creating a stable low end, this time by controlling the bass at its harmonic level. I have another 4-bar loop set up with the kick and bass. The kick is a sample and the bass is generated by Serum. Let's listen. I've created a modified Psytrance bass sample out of a saw wave and loaded it into Serum. If we click the pencil, it will open up Serum's FFT editor. This section at the top is Serum's additive wave editor and gives us control of all the partials that make up the wave. FFT stands for Fast Fourier Transform and forms part of the theory first put forward by Jean-Baptiste Fourier in 1822. He theorized that any waves could be created by adding a number of sine waves. Each of these sine waves are called partials, with the first and lowest known as the fundamental. Partials 2 and onwards are overtones and are integer multiples of the fundamental's frequency. I've now edited this patch so the partials 4 and onwards are on oscillator B, and partials 2 and 3 are together on oscillator A, and the fundamental sub is being generated by the sub oscillator. Now we can control and automate the individual levels of each region of the bass patch. Let's listen as I isolate the first 3 partials while watching the spectrum. But we can go one step further. I've opened Patcher in FL Studio and loaded up 3 copies of Serum, each with 1 layer of the bass patch active. Next, I'm going to route the output of each Serum to a different channel on the mixer. I've also set the keyboard split so each layer has its own region. We can either sidechain duck the bottom layer with the kick or use a keyboard split to place each layer in the piano roll, omitting any sub or mid layer that's overlapping with the kick. This creates a psychoacoustic effect with each top hit and allows the kick sub to breathe. Now we have each layer of the bass on its own channel to process individually. We can set the mix balance of each layer. And apply effects like EQ, compression, and stereo widening. Thanks for watching and see you in the next segment. In this example, I've created a null test. I have 2 identical royalty-free AI tracks on channel 1 and 2. I'm going to flip the polarity of one, causing them to phase cancel and completely null. Next, I've loaded Pro Q3 on channel 1. I've dialed in a 6 dB boost at 12 kHz with a Q of 1. On channel 2, I've got Evo EQ with the exact same settings. But when I flip the polarity, they don't null as expected. There are many reasons why this might happen, so let's have a look at the frequency response in Plugin Doctor. Pro Q3's frequency response matches its interface perfectly. Evo EQ, however, shows an asymmetric curve that looks completely bent out of shape. When boosting near the Nyquist limit, we can see the curve plummeting down to unity gain, causing a huge inconsistency. This is known as EQ cramping. EQ cramping arises from the fundamental mathematics used for symmetrical bell-shaped curves, known as bilinear transform. When mapping an analog filter into the digital domain, the amplitude must be at unity gain at the Nyquist frequency. This is known as frequency warping. Bilinear transform works well across most of the frequency spectrum, but causes issues near the Nyquist limit. One solution is to raise the Nyquist limit by increasing the project sample rate. As we can see with a higher sample rate, EVO-Q response curve is dramatically improved, but this leads to higher CPU and potential latency. Many plugins like ProQ3 and XEQ use unique anti-cramping algorithms. In regards to this, developers' methods are a closely guarded secret. This insert from XEQ's manual sheds a bit of light on this. Another method we can try is to blend a high shelf. With a bit of adjustment, we can almost perfectly match ProQ3's frequency response. This is known as the Masberg method, outlined by Michael Masberg in the paper he wrote in 2011. This is the most likely method developers use to solve cramping. FL Studio's parametric EQ was updated to include an anti-cramping mode. As we can see, the interface shows an accurate frequency response when switching modes. Thanks for watching and see you in the next video.